Welcome to Andes RISC-V Online. This is YiChiang Chang. Today I'm going to cover Andes custom extension to accelerating domain-specific architecture. Andes is the founding platinum member of RISC-V Foundation and also major contributor to RISC-V. We are the chair for several task groups and contribute to a major area of RISC-V ecosystem. We have a more than 1 billion annual run rate and over 1.5 billion last year. And we also have about 300 customers around the world. As a 15 years leading CPU IP company, we have a lot of experience in this field and right now focusing on our V5 core based on RISC-V architecture. Our member also came from many well-known CPU companies such as AMD, DEC, Intel, MIPS, NVIDIA, and Sun, and so on. Andes provides comprehensive product to support our customers. From the top, we have an AndeStar, which now is V5 architecture based on RISC-V ISA. On the top left, we have Ande Core, which is our highly optimized CPU cores. And Ande Shape is our FPGA platform that can help our customer evaluate and validate their SoC design. And on the right-hand side, AndeSight is our IDE tool for designers can easily build their application on our CPU. The next one, AndeSoft, is our BSP, which provide many different software stack. So now let's jump into today's topic. Here's the agenda. First, I will discuss some computing acceleration method, then introduce Andes custom extension that can accelerate domain-specific application. We will show you some AC example and conclude today's webinar with a summary. Let's think about one scenario. Assuming we are looking for standard CPU for our application, we always have to make some trade-off among performance, power, area, or cost. And oftentimes, it's hard to have a standard product that can meet all our requirements. And we really want to have something that can accelerate specific acceleration to fulfill all our needs. So that's why we really need some acceleration to improve our system. If I look at the evolution of computing acceleration, there are 4 major methods. First is the acceleration engine like crypto engine. The second is the coprocessor, for example, GPU. The third one is the ISA expansion, such RISC-V M extension, P extension, or V extension. And the last one is the user extension, like RISC-V Open ISA that allow designer to add custom instruction. Here we list out 4 methods. All of them have their own pros and cons. Some of them have a long start latency. Some of them have the proprietary advantage. For Andes, we picked the most balanced method, user extension, allow user to add custom instructions. And we also provide a powerful tool to help our customer to accelerate their application. And that's why we pick user extension as our strategy to serve our clients. If we take a close look at the acceleration, we can categorize them into 2 parts. One is the data I/O, and the second is compute acceleration. In order to reduce the I/O wait time for data, we can use DNA with double buffer to solve the issue to bring the data close to acceleration unit. And for compute acceleration, our AC Andes custom extension first improve the computation performance like dot product of two vectors or metric convolution. Second, to control existing hardware engine, for example, sending a 90-bit command to external hardware within one cycle. When designers are using the ACE script includes general information of the custom instruction, such as the name, apprend, and custom resource, semantic for the behavior of custom operation, and other information of a custom instruction. The concise Verilog only includes the custom logic provided by ACE designer without worry about other interface signal and control logic related to the CPU pipeline. And with this file, our EDA level tool COPILOT can generate the extended RTL, extended instruction set simulator, and extended tool, and automatically integrate them with the baseline component to create a new CPU and its tools. At the same time, COPILOT can also generate the test environment to cross-check the extended RTL and extended instruction set simulator to help developer to verify their custom instruction. As I mentioned before, COPILOT is an EDA level tool that can help our customer to generate custom instruction. It's highly integrated with the AndeSight, so it can easily to leverage the feature from AndeSight, such as near cycle accurate simulator, software profiling, an intrinsic function or API replacement to use custom instruction, and monitoring the customized instruction when you are debugging. ACE provides many features for designers to design custom instruction that can meet their specific requirements. ACE supports scalar instruction and vector instruction. It also supports background option that can execute the custom instruction parallel from the other instructions. For the apprend, they are used by defining the instruction, also support custom register, custom memory, and custom port, besides from the standard apprend. The imply option can also imply apprend doesn't appear in nominally to reduce the encoding space for custom instructions. Finally, based on custom defined information, ACE can automatically complete tasks of OP code assignment and generate extended components such as tool and simulator. COPILOT can also generate RTL code for instruction decoding, apprend mapping, dependency checking, input access, and output updates. ACE designer can enable logic sharing to save some gatecom and auto-generate waveform control file to jumpstart this simulation based on their needs. Now you have known the ACE feature. Let's take a look at the flow of ACE development. If designers already know the software critical function, they can skip the first step and start to define the custom instruction. Otherwise, designer can profile the application software and find out the time-critical codes. Then the next step is to define the ACE instruction to replace this code and profile again the modified application software to accurately evaluate the performance to see if it can meet the cycle. If not, then repeat the same step until the cycle met. Otherwise, we are ready to move to the next step to implement ACE RTL and evaluate the performance, power, and area. Again, if the PVA requirements are not met, check the RTL and find the room to improve and repeat a step of RTL design. If not, designer need to go back to the software profiling to continue the flow from profile application software until all the requirements are met. For speed up, ACE can easily speed up the performance because you can use one instruction to complete a complicated operation that usually take a lot of cycle. The same idea also applies to power consumptions. With no ACE, an instruction need to go through fetch, decode, retire, plus execute stage for any time. However, with one ACE instruction, you are not only combine and fetch, decode, retire into one time, but also can build a more efficient logic when execute the ACE instruction. And here are a few examples showing how much improvement ACE can enhance your design in terms of performance and power. You can see that with AndeStar with ACE instruction, the more complicated application can get much higher speed up and power efficiency. Here is a simple example to show how ACE instruction can be created. The ACE file provides ACE definition where INSN define the name of the instruction. Operand lists out the name and attribute of the operands that will be used in this ACE instruction. Csync is the scene semantic that will be used by instruction set simulator. And latency is the estimate cycle that this ACE instruction will take in execution. And with this ACE file, ACE can generate the associated intrinsic function. And in this example, the ACC underscore MADD32 is the intrinsic function got generated. The V file contains concise Verilog, where the instruction-specific Verilog logic is enclosed between ACE underscore begin and ACE underscore end. And designers don't need to worry about the rest of the logic such as pipeline control, ACE and baseline CPU interface, and so on, which will be taken care of by our tool automatically. For updating the application C code is very easy too. Designer first find the bottleneck of the code and include a header file in C application. Then replace the C code by auto-generated intrinsic function from COPILOT. And designer can use the markup use underscore ACE to switch and cross-check the performance improvement with and without ACE instruction. ACE also have several features that can help designer to enhance the ACE instruction that I mentioned before. First is that we provide the Andes custom memory and Andes custom register that can see here in the top right. And also another major feature is the converting the scalar instruction to vector instruction. For ACE designer, it is very simple but enhance the ACE script by adding the red part and just leave the rest of the ACE script as the same as a scalar instruction, such as the ceasing, latency, concise Verilog, and instruction is vectorized. ACE also have a powerful feature called background option, which can make the ACE instruction execute parallel from other instructions. Designer just simply add the BG underscore in front of the INSA when you can get the instruction from foreground to background. Same as a vectorizing the ACE instruction. Designer can have the rest of the ACE script as the same as the foreground version, and you are ready to go. Here we show an example of how to use Andes custom port. Let's say designer want to use CPU to directly talk to external hardware through a handshake protocol. Here, CPU will prepare a command through ACR, then send the command to hardware, and wait for the hardware engine ready to send the result back to the CPU. So in the ACE script, designer can define custom ports for 90 bits command that connect to 4 hardware engines, and for 1-bit input ready signal to connect to each hardware engine, and 4 256 bits ports to take the result back from each hardware engine. Logic sharing can also help the designer reduce the hardware gate count. Designer just need to add preset AC_shared in front of the module to enable logic sharing. If designer want to share same hardware, in this case 16 by 16 multiplier, they can name the module using the same name. Otherwise, they can define different name on different module. If designer want to have a different multiplier, they can use parallel. All the control and arbitration logic is automatically handled by ACE to reduce the development effort from the designer. Besides from designing the ACE instruction, how to verify the correctness of designer's logic is very important too in this. Some other tools also generate RTL and simulate the model, but it cannot check the function correctness because it comes from the same source. Designers still need to provide additional model to verify the functionality. And with ACE, the tool will automatically cross-check the functions between the C and concise Verilog provided by designer to make sure their logic is correct. And also, unlike other tools have to learn a new language, ACE script is using the C and Verilog, which designers are familiar. And they can jumpstart to use ACE without additional learning curve and very quick to use the tool to enhance their design. For RTL debugging, our tool can also generate the waveform control file that include the operands and AC interface signal. In this example, you can see operand and signal such as C, V, and IP are included in the waveform. An ACE designer can quickly check the waveform to debug the logic. We also provide System C environment, which support TLN 2.0 for designer to prototype their system. We provide a system CPU module library that include baseline CPU, GDB server, local memory, interface, and so on. And this module can also integrate with other SoC components. Our tool can integrate the ACE into our system module library. And let's say if designer have ACN that need connect to some access interface, ACE will also have this interface in library. So let's look at one more complicated example here that can handle larger amount of data. We would like to improve the inner product of the vector. We assume one is the coefficient as an input that's using the ACR, and there are input data continually loading to the system, and we can use the ACN to take this data. Here we also define the output operand IP using GPR to accumulate the result. The RTL is the same as the previous example. Designer only need to provide the concise Verilog of the inner product of the vectors. And CC is simply multiply two numbers and accumulate results sent as concise Verilog. One thing we have to point out here is that we include a multi-precision library in order to handle the 512 bits variable directly. So by adding one ACE instruction, this function can have 85 times speed up compared to a pure C code. The other case I'm using quite often is the XY memory usage. We can define two XY memory using ACN, and also define the ACR for setting the memory address to implement the ring buffers. The colored part are the additional code in the ACE script to convert the original MADD32 ACE script to ring buffer on XY memory-based architecture. And as you can see in the XY memory points, the address will point to the next data being read out from XY memories. Once the last data read out from the ring buffer, X address and Y address will loop back to the beginning address of these two ring buffers. By using ACE, designer only need to focus on the semantic of a custom instruction. All the housekeeping work related to CPU pipeline has been taken care by COPILOT, such as OP code assignment, decoding, operand mapping, pipeline control logic, and dependence checking for GPR. ACE also have comprehensive support for many types of operand and instruction and verification environments. With ACE, designer can easily turn a highly optimized extendable RISC-V core to become a domain-specific accelerator. This is all for today's webinar. Now we are open for the Q&A session.